Hey, first talk this afternoon, great pleasure to introduce Ben Lowe from University of Chicago. He's going to talk about minimal submanifolds and waste of locally symmetric spaces and maybe higher dimensional expanders.
Oh, yeah. Yeah, thanks for the chance to speak. Really happy to be here. So all of this talk is joint work with Mikolaj Frajcek. So if I don't attribute a theorem, everything is joint work with, or is based on a paper that we wrote together. Yeah, so the starting point for what I'm going to talk about is what I'll call informal conjecture. Due to Gromov, and then I'll also say Larry Guth's name because he's also done a lot of work here, and I first learned about this stuff from survey papers he wrote. So what the conjecture is say we have some space X, which you can think of as a Riemannian manifold or simplicial complex, and we want to assume that it's complicated in some sense. Okay. So then the idea is that every map from X down to a lower dimensional space, we'll say, I guess, lower dimensional Euclidean spaces for this talk. So K is smaller than the dimension of X. The conclusion is that this map has to have a complicated fiber. All right. So another way to say something similar is that is that if we sweep out X by codimension K subsets, then one of those subsets has to be complicated if X is complicated. And in the way that I wrote it here, the sweep out of the way of like sweeping out X, you get would just be coming from taking preimages of points in RK. Okay. Yeah. So that's a pretty vague statement. I'll start making more precise statements soon. But yeah, I think that even in everyday life, there's some evidence, for that like statements like this should be true. So for example, if you have a pair of pants that's too small, then you won't be able to fit them on no matter what you do, right? So I think, hopefully this is at least, I don't know, intuitively plausible that something like this should be true. But maybe surprisingly, not so much is known in this direction, or at least what is known hasn't been so easy to prove. Okay, so I'll talk about some examples now. So the first examples are going to be right, and I also should have said the word waste is in the title of this talk. So what a waste inequality is just an inequality to this effect, right? Where we've chosen some measure or like some quantitative measure of what complicated means, right? So for the first part of this talk, it's going to be area or volume, but you could also choose a lot of other things. Okay. Yeah, so the first examples I want to talk about are the following. So there exist m sub k that are compact hyperbolic manifolds. So they're quotients of hyperbolic space of some dimension by discrete group gamma sub k acting properly discontinuously by isometries. So these are compact hyperbolic manifolds. And so when I say compact in this talk, I'm going to mean compact with no boundary, so I could also have said closed. With a uniform spectral gap for the Laplace-Beltrami operator on just smooth mean zero functions, right? And so how I'm going to write that is just so the bottom eigenvalue for the Laplace-Beltrami operators is just going to be, call it lambda 1, and what I'm saying is that there's some epsilon that's independent of k, so that you have this this uniform spectral gap, right? And so maybe this is known earlier, but at least it I guess worked by Berger and Sarnak implies that you can find these kinds of collections of hyperbolic manifolds where they actually tell you what epsilon is. Like it's something that you can write down and that I think is growing linearly in the dimension, if I'm not wrong. Okay, so I mean that's sort of like one way to say that these M sub k are forming an expander family. Another way that's going to be more relevant for this talk is the following. So I'll just write it with an orange star. And yeah, so it's the following, I guess, consequence of what I just wrote that is at least the same or pretty close to the same. K is just the indexing variable for the family of hyperbolic manifolds that. Yeah, so there's, I should say there exists a, K is just ranging over the positive integers, and all of these are different. Is it okay? Cool. Yeah, sorry about that. Okay, so another, I guess, a consequence of this is that the generic, so I'll say a bit more about what generic means in a second. Generic map from F from M sub k k to R has a large fiber. So it has a fiber F inverse of P, so that the area of the fiber is at least some constant multiple of the volume of the ambient space. Okay, where here C is some universal constant that's just going to depend on the epsilon that I wrote there in a pretty explicit way that I don't remember off the top of my head, like epsilon squared or something, I forget. But the first person to show this, I guess, is Cheeger. Kind of realized there's this like metric geometry interpretation of this. Yeah, so that's the first thing I want to talk about. I do not want to consider all continuous maps because, so area really means, I guess, codimension volume 1 here. So when I want to talk about like the k-dimensional volume of a k submanifold or a k cycle in this talk, I'm just going to say area, and it'll mean that. But but in general, if we have a continuous map, like any kind of a continuous map, then the fibers could be pretty bad. They might not be rectifiable, so we need some kind of condition on the maps in order for this to make sense. Okay? And so one way to do that is just to say that the maps are generic, like they're in some open dense set of maps in some topologies. So you could do like generic smooth maps or generic piecewise linear maps. And that's one way to make it so that, I mean, you can always kind of talk about the areas of the volumes of the fibers and other ways to like require the maps to be real analytic. Yeah, and so I mean, I think like coming up with statements like this that will be true for like any continuous map that might be an interesting question, but I guess it'd be a different kind of mathematics than what this talk is about.
Is there reference, for example, for non-generic maps?
Oh yeah, you could have. I mean, the preimages could be pretty bad. They could be like space filling curves are really bad. Yeah. So if it's a general continuous map. Yeah, I mean, you could even do something stupid like map everything to a point, which okay then. Yeah, I don't know. So there's, just to not have to kind of think about any of that stuff, we require the maps to be generic. So I guess I'll write this adjective in some of the future theorems without comment. Another important point is like for the theorems that we prove with in this talk that are applying to generic maps, it turns out to be enough for the application. So that's another comment. And yeah, so I mean, these sorts of like expander families of hyperbolic manifolds, I mean, they're the only constructions are from number theory. That's how Berger and Starnack are doing them. But then also there are more combinatorial constructions. But I mean, in general, like with the probabilistic methods. But in general, these are hard to construct, and it's kind of hard to get a handle on what the geometry of these sorts of expander manifolds are. I mean, sort of with our kind of Euclidean spatial intuition, we would sort of think of area and volume scaling with different exponents, right? But here it's like they're proportional, so it's a little bit hard to kind of think about what these are. But yeah, so these are an example of expander manifolds. So now I want to talk about higher expander manifolds. So. So a sequence of bounded geometry. Riemannian manifolds. Say m sub n, or n is the indexing variable, that are satisfying the like starred condition that I wrote down. But with instead of R, we have RK. This is going to be called a higher K expander, higher K expander family. Okay, so higher is just referring to the fact that K is going to be bigger than 1, right? So instead of looking at maps down to R, we're looking at maps down to RK. Okay, and so these are harder to construct. Yeah, and so Gromov asked whether these exist, whether do natural higher expander families exists. Okay. So what is so natural and bounded geometry? So what does that mean? So basically it means that they shouldn't be so different from the first example that I showed you. So I mean, for these examples, they're locally isometric to real hyperbolic space of a fixed dimension, right? So the dimensions are all the same, and then like the curvature is uniformly bounded. Yeah, so you can't, I guess, you want kind of nice examples that are not so different from the ones that I just wrote. That's all that bounded geometry and I guess natural mean. Okay, so in the simplicial complex setting, a lot is actually known in this direction. So examples of higher expander, higher K expander, families of simplicial complexes, right? So I guess I haven't exactly said what it means for a family of simplicial complexes to be a higher expander family, but I mean, you can give this definition more or less works, and there are other equivalent definitions for that. So they're due to, so for the K equals 2 case, work by Kaufman, Kajnan, Blavatsky, and then for all K, it's due to Evra and Kaufman. Okay, so that answers Gromov's question in the that I just wrote in the simplicial complex setting. Okay, but in the setting of Riemannian manifolds, the question still there isn't very much progress. So the first theorem that I want to state is progress towards an answer to Gromov's question. So this is again, this is joint work with Nikolai Freichuk. Just call this Riemannian examples of higher expander families. So the theorem is that the collection of all compact or closed Octonionic hyperbolic manifolds, right? So these are quotients of it's called the Octonionic hyperbolic plane by a discrete group gamma in the same way as like the real hyperbolic manifolds we were talking about over there are, quotients by discrete groups. It's just here we have another kind of hyperbolic space. That's the universal cover. And the statement is that these form a 2-expander family. Okay, so what are Octonionic hyperbolic manifolds? So for every division algebra over R, you get hyperbolic spaces. So you have the real hyperbolic spaces, the complex hyperbolic spaces, and the quaternionic hyperbolic spaces, and those all come in infinite families. But then you also have the Octonionic hyperbolic plane. So there isn't an infinite family, there's actually only one. So it's kind of weird, I guess, compared to the other ones. We don't use so much specific to, like, I guess, how these are actually constructed, or, I mean, really what's going into the proof of this theorem, which I'll talk a bit more about at the end, are knowledge of what the unitary representations of the isometry group of the Octonionic hyperbolic plane is, right? So the group of isometries of the Octonionic hyperbolic plane is some exceptional Lie group, which it turns out we know a lot about what the unitary representations are for. And that's one part, and the other key part is just knowledge of the kind of local geometry of the Octonionic hyperbolic plane, in particular what the curvature tensor is. Okay, so I'll come back to that at the end. But first I should say that Bader and Sauer also gave an answer to Gromov's question in the k equals 2 case, in work that appeared a little bit before ours. And they show that towers of covers of M is just some fixed compact Riemannian manifold, are a 2-expander family and then what they need to be true about M is for its fundamental group to have property T. Okay, it's not so important what property T is for this except that, there are a lot of examples, right, where you can construct, infinite towers of covers of Riemannian manifolds over some fixed Riemannian manifold where its fundamental group has property T. So in particular, this is partially including the theorem that we proved as a special case because gamma here will have property T. I guess we're not looking at a fixed family of covers. There are infinitely many commensurability classes here, so in that regard, our theorem is a little more general. But yeah, there's certainly a lot of examples of M where you can construct these towers where you have like a residual finiteness type property that their theorem would apply to, right? So really, theirs is a lot more general.
Just to be clear, the constant, you have a constant that depends only on the Octonionic plane?
Yeah, universal constant for all of them, yep. Right, so that's really important here, yeah. That all the constants for which, these kinds of waist inequalities are true are uniform. So for them, it would be uniform in like the tower of covers, I guess, yeah. Yeah. I don't know. I don't think so. But I haven't, read their paper closely enough to answer that with very much confidence. Yeah, okay, so I mean, so the methods of proof for our theorem and their theorem are pretty different. So they overlap a little bit in that both using representation theory and functional analysis, but in pretty different ways, right? So for their arguments, it's more algebraic and homological. So it's based on filling inequalities where you have one of these maps and you're modifying the fibers by cutting and pasting arguments, and you want to show that if the fibers, if they're too small, then you can show that the fundamental class or a cycle representing the fundamental class is actually a boundary, which can't happen because the fundamental class isn't a boundary. So that's, I don't know, in very broad strokes how their argument works. But for us, I mean, it's really kind of a differential geometry argument. So we're using a lot about the local geometry of these manifolds. And like whereas they're kind of cutting and pasting, we're sort of constructing flows that are pushing the area down and kind of piecing them together in a suitable way. So in very, I guess, broad strokes, that's kind of how the arguments are differing. And just to make another small remark, to say that kind of with our arguments, we can also prove kind of so-called homotopical higher expansion results. And this is related to recent work by Misha here, and then Weinberger. So to briefly just describe an example of like what's like a homotopical higher expansion result. So the kind of thing we could prove is that if we have a branched cover of an Octonionic hyperbolic manifold, right? So some other manifold is branched covering our Octonionic hyperbolic manifold, and then if the branching locus is small, then what we can say is that we can sort of cut out a small codimensional 1 subset so that this branch cover agrees with an actual cover away from that codimensional 1 subset. So really, branch covers with small branching locus have to have been actual covers in disguise. So that's a kind of statement that would sort of fall under this like homotopical higher expansion descriptor. Okay, so I guess that's all I want to say about Octonionic hyperbolic case for now. So I want to talk about a different kind of higher expansion now. Yeah, so for the second theorem, it's also joint with Mikolaj-Rychek. I'll call this topological higher expansion. Right, so going back to the first, like the initial, I guess, conjecture, you have different ways of saying what complicated means, and up to this point, it's been area and volume. But I mean, you can also measure the complexity of the fibers by some topological measure of the complexity. So here we're going to look at the fundamental group. Right, and so the statement is going to be applying to a different family of Riemannian manifolds. So the ones that are quotients of the symmetric space for SL and R. Right, so just SL and R mod its maximal compact subgroup. So for n equals 2, this is the hyperbolic plane. For n bigger than 2, there are these non-positively curved symmetric spaces that I guess aren't quite hyperbolic spaces like the title of the conference, but I guess generalizations of the hyperbolic plane in some sense. So hyperbolic-like spaces. And we're going to let M is going to be just a compact quotient of one of these x by just a discrete subgroup of SO1R acting properly continuously by isometries. So M is compact, gamma is a uniform lattice. Then what the statement is that for every k less than or equal to n over 8 minus 1, what we can say is that every generic piecewise linear map F from M down to Rk has a fiber there's a P such that the map on fundamental groups induced by inclusion from pi 1 of the preimages of P to pi 1 of M has finite index image. So it's virtually pi 1 surjecting. Right? So first comment, what I mean by this inclusion, so F inverse of P might not be connected. What I'm saying is that there's some connected component so that the map on fundamental groups induced by inclusion is virtually pi 1 surjective, right? So that's what the statement is. So this is, the reason I'm calling this like a topological higher expansion result is, so you look at like the inequality for just kind of the like area volume expansion. It's like the fibers are kind of as large as the ambient space in the sense of like area and volume, right? So here there's like some fiber that's as large as the ambient space in the sense of like fundamental group. So its fundamental group is including to a finite index subgroup of pi 1 of M. Right. And so I guess in the next talk you'll kind of see how, for real hyperbolic spaces like these kinds of real hyperbolic manifolds, these kinds of statements will fail very drastically, like for hyperbolic manifolds that are fibering over the circle. But in the higher rank setting, it's I guess very different in that regard. Okay. So I want to make some comments about that. So erase. Yeah. Any questions so far, or? Good. Okay. Oh, so first I'll state a corollary. So. Simplicial isometric actions of gamma as in the previous theorem. On k-dimensional cat 0 simplicial complexes are very constrained in the sense that they all have to have some point that every element of the group is fixing. So they have a global fixed point. For k in the same range, so it's like most n over 8 minus 1. Okay. Right, so the first thing I should say is that, so cat 0, really what you think this is meaning is it's a kind of non-positive curvature condition, so it's like saying these are tree-like, so these are supposed to be the higher dimensional analogs of trees. Okay? And so the k equals 1 case of this statement would be that gamma doesn't act on a tree without a global fixed point. And for SO3R, that's due to Serre. For SO1R for n bigger than 3, that's due to Margulis. And so one thing you can ask is, okay, can you do better for n larger? Can you prove some kind of a stronger statement? For lattices in SO1R as n's getting bigger, and so that's this corollary is saying that actually you can, that actions on these kind of like higher dimensional analogs of trees are very constrained. And I should have said contractible here. Yeah, sorry, I forgot to say that. Okay, so if you know about property T, then this corollary is something in the direction of like a higher property T. Another way to think about this is, non-positively curved simplicial complex that gamma acts on in the most natural way is just SL and R mod SO1R is just X, right? And so that's it's gonna act on X in kind of a way that satisfies all these conditions, right? And so then you can ask like, okay, so can we find lower dimensional spaces that gamma is acting on in a similar way? And this corollary is saying that if you make the dimension low enough, then actually you can. Okay. Any questions?
Should it be virtually or find it like something?
Yeah. It would be virtually if I didn't have cat 0. Cat 0, if you have a finite orbit, then you get a global fixed point. So there's also a statement if I just remove cat 0 and then say it's a simplicial action on a contractible manifold, I think, or contractible simplicial complex, if I understood the question correctly. Thanks. Great. Okay, so I should make some comments here. So the non-uniform case of the corollary is due to Benson Farb, and he gets a better range of dimensions. He gets, I think, all the way up to dimension n minus 3. We get a range that's linear in n, but yeah, it's pretty. He gets a better number here definitely, and then but he's really using the kind of structure at infinity in an important way in what he's doing to get global fixed points. And then another remark is, so I should say that this is using recent work by Connell, McReynolds, and Wong in a really important way. That's one of the key inputs in this corollary and also the theorem that I just wrote. And And then a related theorem that I want to state that's essentially due to Cannell, McReynolds, and Wong, but it's like their work plus a computation that like we do with Mikolai is the following, which is that if gamma inside S1R is it's discrete, and maybe I should say torsion free too, just to be safe, and then infinite covolume. Right, so not a lattice, right? When we model by gamma, we get something with infinite volume. Then we can prove the following. Following vanishing theorem is true for the cohomology of just X mod gamma with any coefficients in any ring. This is equal to 0 for k above the dimension of X minus this same range. So shoot, ran out of room. Minus n over 8 minus 1. Okay. So the X mod gamma really has to be, I guess, a space with kind of homological dimension much smaller than the dimension of X if n is large, right? So yeah, so if we assume gamma doesn't have any parabolic elements, right? Then what this is saying is that if gamma is a lattice with no parabolic elements, so if it's just a uniform lattice, then I mean the homological dimension of X mod gamma will be just the dimension of X, right? But then if you're infinite covolume, the dimension is going to have to drop by this. The homological dimension is going to have to drop by an amount that's linear in n, right? So there's this sort of gap theorem for infinite covolume versus finite or uniform lattices in SLNR. That seems to be related to these kinds of higher expansion statements that I've been talking about, but in a way that isn't fully fleshed out yet. Okay, any questions or yeah?
Is what you do really specific to the symmetric space, or is the range just using the space?
Yeah, so we did the computations just for that, but it should also work for I think like SOPQ and other higher rank ones. Yeah. We haven't done the computations yet for those, but yeah, for our paper we just focused on the SONR case. Yeah, that's a good question. Maybe for the case where the universal cover is reducible, it might be. I'm less sure there. Like products of SONR, I don't know, but for the irreducible ones, I think irreducible symmetric spaces, I think, yeah. Great. Okay, so in the remaining time, what I want to do is talk a little bit about the proof of this first theorem that I stated. So just to briefly talk about some of the ideas that go into the proof of theorem 1, but in a very pretty incomplete way. Okay, so what's our starting point? So we have a map from F, or map F from M, which is the quotient of Octonionic hyperbolic plane. And we're mapping it down to R2, right? So we have a map from this, I guess, 16-dimensional Riemannian manifold down to R2. Okay. And then how we want to think of this is that this is going to give us what's called, I'm going to make a formal definition of this concept, but it's what's called like a sweep out of M by just taking a point in R2 to map to its preimage, right? So I mean, F is some piecewise linear generic map down to R2, or just generic in the sense that it kind of the fibers are nice enough that we can talk about their areas. And what we're doing is for each point, we take its preimage in M, and we think of those as kind of sweeping out our manifold. Okay. All right. So then there's this thing called the Almgren Pitts min-max theory, which is going to gives what's called a minimal submanifold in quotation marks, or quotation on the submanifold. Such that minimal submanifold, I'll just give it a color S, such that the area of S is going to be at most the supremal area of one of the preimages. Okay, so first I should say what does it mean that S is minimal, and then I'll say what's going on here with this statement, using a huge black box I guess, but I'll explain what it means. So what this is meaning is that we're locally area minimizing. So deformations of S in small balls don't decrease area. Okay. And so what this Almgren-Pitts min-max theory is doing is it's sort of like letting us pull this sweep out tight to get a minimal surface. So I'll draw a picture to explain what that means. So let's pretend that M is just S2, and that we're, instead of mapping to R2, we're just mapping to R. So what we have then is that our preimages would be, I don't know, giving us these curves inside the round sphere, right? So in this case, the preimages would just be kind of sweeping out S2 by these cycles that I've drawn. Right. And so then what this like min-max process would give us here is it would give us it would just give us the copy of the equator, right? Which is a one-dimensional minimal submanifold, right? So we sort of pull this sweep out tight, and we get a minimal submanifold, which in this case is just a geodesic, right? And so this like statement about in small balls you don't decrease area. It's true here because even though you can sort of like push everything to the North Pole, that will make the length go down or make the area go down. If you try to make the length go down in sort of a small ball, you can't actually do that. Okay. So that's how we sort of have this kind of like pull tight min-max procedure, and that gives us a minimal submanifold. So the shot here So what is the upshot? So what we've reduced ourselves to showing is that every codimension 2 minimal submanifold of M has area that's up to universal constants proportional to the volume of M. Okay, and so what we gain here is that there's a really rich and well-developed theory of minimal submanifolds that we can kind of draw on now. So that's why this reduction is helping us. And I should have said also like submanifold in quotation marks. So the thing we get is something that's less regular than a submanifold, but still regular enough that we can do calculus on it in the way that we'll need to for the proof. So that's, yeah, so you can basically kind of think of this as more or less a submanifold. Okay, so let me just say a couple words about where we go from here, then I'll end the talk. So what we want to do, we're going to look at the indicator function, the lift of S to G mod gamma, right? So we want to just work instead of in X mod gamma, which is G mod gamma gamma, we want to work in G mod gamma. R, just be the indicator function of S. Okay, and then we want to smooth this indicator function out a little bit, so we get kind of a better function to work with. So if we just kind of convolve against like a small bump function, we smooth out S, we get this like smooth function that's a little nicer, but also kind of contains all the information we care about S, right? And so then the thing that we want to look at is we want to look at an integral with the ball of radius r centered at the identity of action of G on U, inner product with U, and then just integrating. And this is the L2 inner product, L2 of G mod gamma, integrating over just this ball inside G, right? So we have G is acting on G mod gamma in a way that's preserving the volume. So then we get an action of G on L2 of G mod gamma, right, by unitary transformations, right? And then if we look at the matrix coefficients for that representation of G and L2 of G mod gamma, right, it's just these L2 inner products, okay? And then we want to look at all of them at once. It turns out, I guess that's not obvious in advance. And then how the rest of the proof is going to go from here, right? So we started with our minimal submanifold, and we've made it into a smooth function, which we've made into all these matrix coefficients. So on the one hand, we're going to use facts about like how fast the mean zero part of U is going to be decaying as G goes to infinity, right? So that's coming from the knowledge of what all of the unitary representations of G are. And on the other hand, we're going to rewrite this. We're going to kind of like, this is really a double integral. So if we kind of, because this inner product's an integral. So if we switch the integrals, then what we end up looking at here is basically just the volume growth of lifts of S to the universal cover. So lifts of S to just the Octonionic hyperbolic plane. And then there's something called the monotonicity formula in the theory of minimal surfaces that we can sort of get a much better version of in the Octonionic hyperbolic plane. Yeah, and so kind of it ends up just the numbers work out, and then this is sort of the case where we're able to kind of get get the statement we want at the end. We kind of do the computation here. So I'll end my talk now. Thanks for listening.